Welcome back. We now have three solving methods: separation, the integrating factor for linear equations, and the exactness method. Today we add a meta method, a strategy that recycles all of them. The idea is ancient and powerful. When an equation is hard in the variables you have, change to better variables. Two substitutions do an enormous amount of work. The first handles homogeneous equations, where the right-hand side depends only on the ratio y over x. We substitute v equals y over x, and the equation becomes separable. The second handles Bernoulli equations, which carry a nasty nonlinear y to the n term. We substitute v equals y to the 1 minus n power, and the equation becomes linear, ready for the integrating factor. In both cases, the philosophy is identical. Transform the hard problem into an easy one we have already mastered. Solve it, then transform back to the original variable. Let us see both in action. Start with homogeneous equations, and let me flag a warning right away. The word homogeneous is overloaded in this subject. 2 episodes ago, homogeneous meant the linear equation had q equal to 0. Today it means something completely different, so keep them separate in your mind. Here, a first-order equation is called homogeneous if you can write the derivative dy dx as a function, f of the single ratio y over x. The right-hand side is allowed to depend on x and y, but only through their ratio. A quick way to spot this when the equation is in the m dx plus n dy form, it is homogeneous when m and n are homogeneous of the same degree, meaning if you scale both x and y by a factor t, you can pull out a common power of t from each. When the equation has that ratio structure, a single substitution will collapse it into something separable, as we will see next. Here is the substitution and why it works. Let v equal y over x, then y equals v times x. Since v is itself a function of x, we differentiate y as a product, dy dx equals v plus x times dv dx. That is the product rule, with the derivative of x being 1. Now substitute this into the equation dy dx equals f of v. The left side becomes v plus x dv dx, and the right side is f of v. Subtract v from both sides, x times dv dx equals f of v minus v, and look what happened. The right side is now a function of v alone, and the left side neatly splits x and v. Divide and rearrange dv over the quantity f of v minus v equals dx over x. That is a separable equation, exactly the kind we solved in episode 3. Integrate both sides, then at the very end substitute v equals y over x to return to the original variable. The ratio structure of a homogeneous equation is precisely what makes this separation happen. Let me show you the hidden symmetry that makes the substitution natural. This is a slope field for a homogeneous equation. Draw any straight ray from the origin outward. Along that single ray, the ratio y over x is constant because both coordinates scale together, and since the slope depends only on that ratio, every little slope dash along the ray points in the same direction. The slope field is constant along rays from the origin. That is a radial symmetry. The solution curves, drawn to the field, turn out to be self-similar. Zoom in or out from the origin and you see scaled copies of the same shape. This is exactly the structure the substitution v equals y over x is built to exploit. By switching to v, the ratio, as our new unknown, we are aligning our variable with the natural symmetry of the problem, and the equation gratefully simplifies into a separable one. Let us solve one. The equation is dy dx equals the quantity x plus y over x. First rewrite the right side in terms of the ratio. X plus y over x splits into x over x plus y over x, which is 1 plus y over x, that is 1 plus v, so it is homogeneous with f of v equal to 1 plus v. Now substitute dy dx equals v plus x times dv dx. The equation becomes v plus xv prime equals 1 plus v. The v terms on both sides cancel, leaving x times dv dx equals 1. Beautifully simple and separable. Write dv equals dx over x. Integrate both sides, v equals the natural log of the absolute value of x plus a constant c. Finally, substitute back v equals y over x, so y over x equals log of the absolute value of x plus c. Multiply through by x, y equals x times the quantity log of the absolute value of x plus c. That is the general solution, found by turning a non-separable equation into a separable one. Before Bernoulli, a subtlety worth flagging, because it is a place real solutions get lost. When we separated the homogeneous equation, we divided by the quantity f of v minus b. Dividing is only legal when that quantity is not 0. But suppose there is a constant value v0 where f of v0 equals v0. Then v identically equal to v0 is itself a perfectly good solution, and in the original variables, that is y equals b0 times x, a straight line through the origin. The division step silently threw it away. So whenever you separate by dividing, pause and ask what constant values you divided by, and check each one as a possible solution in its own right. This is the same caution you met with separable equations. Divide and can drop the equilibrium solutions. Find them separately and report them alongside the general solution. Now the second workhorse, the Bernoulli equation. It looks almost linear, y prime plus p of x times y equals q of x times y to the n. The only troublemaker is that y to the n on the right, where n is some power. Two values of n are not really troublemakers. If n is 0, the right side is just q, and the equation is already linear, solvable with the integrating factor. If n is 1, the right side is q times y, which combines with the left and makes the equation separable. So those cases need nothing new. But for any other n, including fractions and negative numbers, that y to the n term genuinely breaks linearity, and none of our methods apply directly. Our goal is to find a substitution that annihilates the y to the n term and leaves behind a clean linear equation and a new variable. Then we bring in the integrating factor from episode 4 to finish. Remarkably, one specific substitution does exactly this, every time. Here is the substitution that performs the miracle. Let v equal y to the 1 minus n power. Differentiate with the chain rule, v prime equals 1 minus n times y to the minus n times y prime. Hold that, now take the Bernoulli equation and divide every term by y to the n. The left side becomes y to the minus n times y prime plus p times y to the 1 minus n. The right side becomes just q. Now recognize the pieces in terms of v. The term y to the 1 minus n is exactly v, and the term y to the minus n times y prime is exactly v prime divided by 1 minus n from our chain rule. Substitute both. We get v prime over 1 minus n plus p times v equals q. Multiply through by 1 minus n, and we land on v prime plus the quantity 1 minus n times p times v equals 1 minus n times q. That is a first-order linear equation in v. The nonlinear term has vanished completely. Solve it with the integrating factor, then raise v back to the 1 over 1 minus n power to recover y. Here is the whole Bernoulli strategy as a single map. Start in the top box, the nonlinear world, with the equation y prime plus py equals q times y to the n. We cannot solve it here. Follow the golden arrow downward labeled with the substitution v equals y to the 1 minus n. That carries us into the second box, the linear world, where the equation reads v prime plus the quantity 1 minus n times p times v equals 1 minus n times q. This box we can solve with the integrating factor from episode 4. Once we have v as a function of x, we follow the arrow back upward, labeled y equals v to the 1 over 1 minus n, which undoes the substitution and delivers the original unknown y in the third box. The shape of the diagram is the whole philosophy of substitution: leave the hard world, solve in the easy world, and return. Every substitution method in differential equations is some version of this round trip. Let us run a full Bernoulli example. The equation is y prime plus 1 over x times y equals x times y squared. Read off the parts. P is 1 over x, q is x, and n is 2. So the substitution is b equals y to the 1 minus 2, which is y to the minus 1, the reciprocal of y. Since 1 minus n is minus 1, the transformed linear equation is b prime plus minus 1 times 1 over x times v equals minus 1 times x. That simplifies to v prime minus 1 over x times b equals minus x. Now use the integrating factor. Here the coefficient is minus 1 over x, and its integral is minus log x, so mu is e to the minus log x, which is 1 over x. Multiply through, the left side becomes the derivative of 1 over x times v equal to minus 1. Integrate 1 over x times v equals minus x plus c. Multiply by x, v equals minus x squared plus cx. Finally recover y, which is 1 over v, since v was y to the minus 1, so y equals 1 over the quantity cx minus x squared. That is the general solution, nonlinear equation cracked by linearization. One more, to show the method handles fractional powers without complaint. The equation is y prime plus y equals the square root of y, that is, y to the 1/2. So p is 1, q is 1, and n is 1/2. The substitution is v equals y to the 1 minus 1/2, which is y to the 1/2, the square root of y, and 1 minus n is also 1/2. The transformed linear equation is b prime plus 1/2 v equals 1/2. The integrating factor, with coefficient 1/2, is e to the x over 2. Multiply, the left side is the derivative of e to the x over 2 times b equal to 1/2 e to the x over 2. Integrate the right side to get e to the x over 2 plus c. Divide by the factor, v equals 1 plus ce to the minus x over 2. Finally, recover y. Since v was the square root of y, we square, y equals the quantity 1 plus ce to the minus x over 2, all squared, a fractional Bernoulli power handled by exactly the same machinery. Recognize n, substitute, solve the linear equation, raise back. The two substitutions we featured are the stars, but the underlying strategy is far more general, and it is worth knowing a few cousins. If your equation has the form y prime equals some function of the combination ax plus by plus c, then substituting v equals that whole linear combination reduces it to a separable equation. If you see a y over x structure but shifted away from the origin, you can translate the coordinate system first to recenter it, then apply v equals y over x as usual. And much later, when we reach second-order equations, a substitution called reduction of order lets you set p equal to y prime whenever the unknown y itself does not appear. The meta-lesson is the important takeaway. There is no single universal substitution. Instead, you look at the structure of the equation and choose a substitution that matches it, developing an eye for that structure, recognizing a ratio, a linear combination, a hidden power is the real skill, and it pays off across all of mathematics. Finally, two checks that should become reflex after any substitution problem. First, did you actually transform back? It is easy to solve the easy equation for v and then forget to return to the original variable. Your final answer must be expressed in terms of y, not left sitting as v. That one undone step is the single most common error in these problems. Second, does your answer satisfy the original equation? Differentiate the y you found and plug it back into the starting differential equation. If both sides agree, you are done with confidence. For our Bernoulli example, where y came out as 1 over the quantity cx minus x squared, you can differentiate and verify that y prime plus 1 over x times y really does collapse to x times y squared. And remember any equilibrium or straight line solutions you set aside earlier while dividing, report those too. Transform, solve, transform back, and verify. That discipline turns a clever trick into a reliable method. A little history, and it is a colorful one. The Bernoulli equation is named for Jacob Bernoulli, who posed it in 1695 as a public challenge problem, daring his peers to solve it. His younger brother Johann Bernoulli, who was also his lifelong bitter rival, solved it, and so did Leibniz, both arriving at the linearizing substitution we use today. The Bernoulli family was extraordinary. Across a few generations, it produced 8 mathematicians of note, and the relentless, often nasty competition between Jacob and Johann actually pushed early calculus forward at remarkable speed. It is worth appreciating that the substitution v equals y to the 1 minus n is one of the earliest recorded examples of a now universal idea: linearize a hard problem by a clever change of variable. That single strategy, transformed to a world where the problem is linear, echoes through all of modern mathematics, from differential equations to machine learning. It started, in part, with two feuding brothers. Let us recap. The strategy this episode is a single idea: transform a hard equation into an easy one, solve the easy one, and transform back. For homogeneous equations, where the derivative equals a function of the ratio y over x, we substitute v equals y over x and obtain x times v prime equals f of v minus v, which is separable. Our example, dy dx equals x plus y over x, gave y equals x times the quantity log of the absolute value of x plus c. For Bernoulli equations, y prime plus py equals q times y to the n with n not 0 or 1, we substitute v equals y to the 1 minus n and obtain a linear equation. V prime plus the quantity 1 minus n times p times v equals 1 minus n times q, which we finish with the integrating factor from episode 4. Our example, y prime plus 1 over x times y equals xy squared, gave y equals 1 over cx minus x squared. Historically, the equation traces to the feuding Bernoulli brothers and Leibniz. Next episode, we stop solving and start asking the deep questions. When does a solution exist? When is it unique? And what can we say about long-term behavior without solving at all? Today, we solved hard equations by changing variables. The strategy is always the same: transform a problem you cannot solve into one you can, solve it, then transform back. First, homogeneous equations, where the right side depends only on the ratio y over x. We substitute v equals y over x, which means y equals v times x. Differentiating with the product rule and substituting turns the equation into a separable one in v and x, which we already know how to finish. Second, Bernoulli equations, which look like y prime plus p of x times y equals q of x times y to the n. That y to the n term destroys linearity. The cure is the substitution v equals y to the 1 minus n power. After differentiating and rearranging, the nonlinear term cancels perfectly, and you are left with a first-order linear equation in v, which the integrating factor cracks. Once you find v, you raise it back to recover y. 2 substitutions, 1 philosophy. Next time, we stop solving and start asking the deep questions. When does a solution exist? When is it unique? And what can we learn about a system's long-term behavior without solving the equation at all? If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.